An F-unit cab is the first place in American railroad history where one engineer could control more horsepower than 4 steam locomotive crews combined. The throttle moves through 8 positions: idle, and then notches 1 through 8. Each notch increases prime mover RPM and electrical output by a specific increment. Hold the handle at notch 8, and you are commanding 2,000 horsepower from a single locomotive, or 8,000 horsepower from a 4-unit consist coupled behind the lead cab. The engineer in the lead F-unit controls every locomotive in the consist through a single 27-pin electrical jumper. Every throttle change, every brake application, every dynamic brake engagement. This is what it was like to actually drive the locomotive that ended American steam. The procedures, the controls, the operational experience that made the F-unit not just a more efficient locomotive, but a fundamentally different job. The engineering changed the machine. The operating changed the profession. A steam locomotive required 2 operators. The engineer controlled the throttle, the reverser, and the brakes. The fireman managed the boiler, coal, water, and the constant adjustment of steam pressure that kept the locomotive alive. An F-unit required 1. The fireman position remained in the cab through the union contracts of the dieselization era. But the work that had defined the fireman's role for a century was gone. There was no boiler to feed. There was no fire to maintain. The diesel prime mover ran on its own. And because the F-unit used electrical control rather than mechanical control, multiple locomotives could be coupled together and operated as a single unit from a single cab. An engineer in a lead F-unit was not operating 1 locomotive. They were operating 2, 3, or 4 locomotives simultaneously, with the same control inputs commanding every prime mover in the consist. What it was like to drive an F-unit is the story of how this transformation happened, and what the engineers who actually did the work experienced when they sat down in the cab. The F-unit control stand was a revolution in locomotive operation, where a steam locomotive presented the engineer with dozens of valves, levers, gauges, and controls scattered across the entire cab. The F-unit control stand consolidated everything into a single integrated panel directly in front of the engineer's seat. The engineer sat on the right side of the cab. The control stand was positioned for natural hand placement: throttle on the right, automatic brake valve in the center, independent brake valve to the left. Every primary control was within arm's reach without leaning, standing, or turning. The throttle handle moved through a defined arc with 8 detent positions. Idle was the lowest. Notch 8 was the highest. Between positions, the engineer could feel a mechanical click as the handle locked into each notch, a tactile confirmation of the throttle position even without looking at the indicator. At idle, the prime mover spun at approximately 300 revolutions per minute, producing minimal output. At notch 8, the prime mover spun at approximately 800 revolutions per minute, producing full-rated horsepower. The progression was non-linear. Each notch increase produced a larger output jump than the previous notch. The engineer monitored the locomotive's actual electrical output through an ammeter that displayed traction motor current. The ammeter was the most watched gauge on the control panel. The engineer used it to confirm that the throttle position was producing the expected electrical output, to detect wheel slip before it became destructive, and to manage the locomotive's load on grades. The brake stand contained 2 separate valves. The automatic brake valve controlled the air brakes on every car in the train, plus the locomotive brakes. The independent brake valve controlled only the locomotive brakes. The engineer used the independent brake for slow yard movements and for holding the locomotive stationary while releasing the train brakes. The air brake system worked by reduction. The brake pipe ran the length of the train at 70 to 90 pounds per square inch. Reducing the pipe pressure caused the brakes to apply. Restoring the pressure caused the brakes to release. The automatic brake valve allowed the engineer to make incremental reductions: minimum reductions of 5 to 7 pounds, service reductions for normal stops, full service reductions for harder stops, and emergency reductions that dumped the entire brake pipe pressure for immediate maximum braking. But the F-unit had one control that no steam locomotive ever had, and it changed how trains descended mountains. The dynamic brake reversed the function of the traction motors. In normal operation, the motors received electrical current from the main generator and converted it into mechanical force at the wheels. In dynamic braking, the wheels drove the motors as generators, converting the train's momentum back into electrical energy. That electrical energy had to go somewhere. The F-unit dissipated it through resistor grids mounted on the locomotive roof. Large blocks of high-resistance wire that turned the recovered electrical energy into heat. On hard dynamic braking, the resistor grids would glow visibly red. The dynamic brake was most effective at moderate speeds, roughly 20 to 40 miles per hour. Below 20, the traction motors generated insufficient current to produce meaningful braking force. Above 40, the resistor grids approached their thermal limit, and the brake had to be modulated to avoid overheating. The engineer activated the dynamic brake through a selector lever and a separate dynamic brake handle. The selector lever switched the traction motors from motor mode to generator mode. The handle controlled the braking force, equivalent to the throttle handle but applying retarding force rather than driving force. On mountain descents, the dynamic brake transformed the experience of operating a locomotive. A steam locomotive descending a grade had to use friction brakes continuously, wearing brake shoes and risking thermal failure of the brake equipment. An F-unit could descend the same grade with the friction brakes barely engaged, using dynamic braking to absorb most of the descent energy. The Western railroads, Southern Pacific, Union Pacific, Western Pacific, built their dieselization economics partly around dynamic braking. The Sierra Nevada grades, the Rocky Mountain crossings, the Cascade routes. Every major mountain crossing in the American West became dramatically easier to operate after F-units arrived. Brake shoe consumption dropped by 80% or more on mountain routes. Brake equipment failures declined dramatically. The runaway train hazard that had defined Western railroading for a century became a manageable risk rather than an existential threat. And the F-unit did something else no steam locomotive ever managed. It made multiple locomotives feel like one. Multiple unit operation, universally called MU operation, was the F-unit's defining operational advantage. 2, 3, or 4 F-units could be coupled together and controlled from a single cab through a single electrical jumper cable that ran between every locomotive in the consist. The jumper carried the electrical signals that commanded each locomotive's throttle position, dynamic brake setting, sanders, headlight, and horn. The lead unit's engineer sent commands. Every coupled unit received the same commands simultaneously. Each unit's prime mover responded independently to those commands. When the engineer notched the throttle from idle to notch 4, every prime mover in the consist responded together. 4 prime movers spinning up, 4 generators producing current, 16 traction motors applying power to the rails, all from a single throttle handle in the lead cab. This had no precedent in steam operation. 2 steam locomotives coupled together as a double header required 2 crews, 2 engineers, and 2 firemen, operating their locomotives in coordination through visual signals and whistle communications. The crews had to anticipate each other's movements. Mistakes produced bucking, slipping, or coupler damage. An F-unit ABBA consist, 4 locomotives, required exactly the same crew as a single F-unit. 1 engineer and 1 fireman. 8,000 horsepower of locomotive controlled by 2 people. The labor savings compared to equivalent steam operation were transformational. A typical mainline freight assignment in the F-unit era used 3 or 4 units coupled together. Some long-haul assignments used 5. The crew loaded into the lead unit at the originating terminal, ran the entire consist as a single locomotive across hundreds of miles, and handed off to a relief crew at a division point. The mechanics of crew change were also simpler. Steam locomotives required servicing at every crew change: water, coal, ash removal, mechanical inspection. F-units required minimal servicing between runs, fuel, and basic inspection. The relief crew could be moving the train within minutes of taking over. Yard movements in F-units were also distinctly different. The independent brake, controlling only the locomotive brakes, allowed precise low-speed positioning that steam locomotives could not match. Switching crews learned to spot cars within inches using the independent brake and throttle modulation alone. The actual experience of driving an F-unit was, by the standards of steam operation, almost unrecognizable. The cab was quieter. The cab was cooler. The cab was cleaner. The engineer's seat was positioned for hours of continuous operation, rather than the cramped, hot, dirty conditions that defined steam cab work. The visibility forward was exceptional. The streamlined nose of the F-unit gave the engineer a panoramic view of the track ahead. The 4 porthole windows on each side provided peripheral awareness. The vertical windshields could be opened for ventilation in summer, or closed against weather. The instrumentation was straightforward. The ammeter for traction motor current. The brake pipe gauge for train brake pressure. The independent brake gauge for locomotive brake pressure. The speedometer. The sander and signal repeaters. Every gauge had a single clear purpose. Every gauge was positioned for natural eye movement from the forward view. And the F-unit was equipped with two-way radio communication, a capability that steam locomotives rarely had and that diesels integrated as standard equipment from the late 1940s onward. The engineer could communicate with the conductor in the caboose, with the dispatcher, with the yardmaster at the destination terminal. The operational coordination that defined modern American railroading became possible because the F-unit had the cab space and electrical capacity to support radio equipment as standard fitment. Engineers who transitioned from steam to F-units described the experience in remarkably consistent terms. The work became less physical and more mental. The locomotive demanded less attention to its own internal state, no boiler pressure to monitor, no fire to maintain, no water to manage, and more attention to the operational environment. Signals, track conditions, train handling, communication. The skills that defined a competent F-unit engineer were different from the skills that defined a competent steam engineer. Less mechanical sympathy with the locomotive itself. More awareness of train dynamics. Better signal observation. More precise brake handling at the slow speeds that yard and terminal operations demanded. But the deepest change was psychological. A steam locomotive was a living machine. It required constant tending. Its performance varied with the fire, the water, the coal quality, the weather. An F-unit was a tool. It started reliably. It performed predictably. It demanded competence rather than craftsmanship. Engineers who had spent decades as steam engineers found the transition complicated. Some welcomed it. The reduced physical demand, the cleaner working environment, the simpler operation. Others mourned what they had lost. The intimate relationship with the machine, the skill differentiation, the pride of mastering a complex thermodynamic system through years of accumulated experience. The F-unit ended steam locomotion in America not just through engineering and economics, but through the operational experience it offered. The locomotive that anyone could learn to operate competently. The locomotive that turned an art into a profession. Driving an F-unit was the experience of operating American railroading's first modern locomotive. Consolidated controls, multiple unit operation, dynamic braking, radio communication. Every operational technique that defines modern American freight railroading was either invented for the F-unit or perfected in it. This is part 3 of our From the Cab series, exploring how the most significant locomotives in American railroad history were actually operated. Companion to our What's Under the Hood series on the engineering inside each locomotive. Both series are linked in the description. Part 4 covers driving the Pennsylvania Railroad K4 Pacific, the steam locomotive that defined an era of American passenger railroading through the operational skill of the engineers and firemen who ran it. A locomotive that demanded everything from its crew and rewarded competence with one of the most respected jobs in American industry. Subscribe so you do not miss it. There are more locomotives to examine. There are more cabs to climb into. We will keep telling the story of how the machines were actually operated by the people who work them.